All right, Physics 210 students. So our first video for Chapter 12, we're going to talk about flow rate and its relation to velocity, which is covered in Chapter 12.1. Okay, so first off, so now remember Chapter 12, we're talking about fluids in motion, so fluid dynamics. And one of the useful things here is something called the volume flow rate. So essentially imagine you're watching some fluid flow down, I don't know, pipe, channel, whatever it is. But what you do is you measure the volume of fluid that passes a point in a specific amount of time, and that defines your volume flow rate. And we're going to use, the textbook uses a capital Q to stand for this volume flow rate. Now, if you do a little bit of algebra, you can show that this volume flow rate, so volume per time, you can also write as the area of the pipe or tube the fluid is flowing through times the velocity of the fluid at that point. So we can write, volume flow rate is the area of the cross-sectional area of the pipe or the channel or the tube you're flowing through times the velocity, or really the speed actually. Okay, so now the key thing here is something called the continuity equation. And the continuity equation is really just about the conservation of mass. So essentially, right, if you imagine you have some sort of a pipe, so if fluid goes in one end, well, it has to come out the other end, right? So this mass, the fluid itself, the mass of the fluid doesn't just mystically disappear or appear. So what this means is that if we have an incompressible fluid, so generally that means a liquid. So the continuity equation says that the volume flow rate must be constant. So the volume per time flowing through one point must equal the volume per time flowing through at another point. And again, we can rewrite that as, we set our volume flow rate, we could write as the area times the speed. So the area times speed at one point equals the area times speed at some other point. And the consequence of this, so if you have a pipe, fluid flowing through a pipe, and if the size of the pipe changes, it means the speed of the fluid also has to change. Specifically, if the area, the size of the pipe gets smaller, then the speed of the fluid has to get bigger. And again, that's so that the volume flow rate stays constant. Okay, so let's do a quick example and see how this works. So we have a nozzle with a radius of 0.25 centimeters attached to a garden hose with a radius of 0.9 centimeters. Flow rate through the hose and nozzle is 0.5 liters per second. Calculate the average speed of the water. Okay, so we have a volume flow rate, 0.500 liters per second. But of course, liters per second isn't our standard units because it's volume per time, and we typically measure volume in cubic meters. So over here, I actually just went ahead, and since I knew I was going to have to convert, I did the conversion for the volume flow rate. So 1 liter is 0.001 cubic meters. So you do the conversion, and our volume flow rate is 5 times 10 to the minus 4 cubic meters per second. Okay, so now if I look in the hose, so volume flow rate in the hose is going to be, so I'll put a little h here, is going to be the cross-sectional area of the hose times the speed of the fluid in the hose. And I know my volume flow rate is 5 times 10 to the 4 cubic meters per second. So I can write this, so let's do 5 times, actually I've got 3 sig figs I believe, 10 to the minus 4 cubic meters per second is going to equal the area. And well, if I assume this is a cylindrical channel here, so the area is going to be the area of a circle, so pi r squared. And let's see, the hose has a radius of 0.9 centimeters, or 0.9 times 10 to the minus 2 meters squared. So that's my area, pi r squared, times whatever the speed of the fluid in the hose is. So now I just have to solve that for the speed. So if I take 5 times 10 to the minus 4, divide by pi, and divide by 0.9 10 to the minus 2 squared. So, and I've got 3 sig figs it looks like, so 1.96 meters per second. Okay, so now we do the exact same thing in the nozzle. So in the nozzle, well, volume flow rate in the nozzle is going to be the radius, or sorry, the area of the nozzle times the velocity of the fluid in the nozzle. Now, continuity equation says that the volume flow rate has to stay the same. So I've got the same volume flow rate, 5 times 10 to the minus 4 cubic meters per second. That's going to be the area. Again, if this is a circular cross-section, area is going to be pi r squared. So pi times 0.25 10 to the minus 2 meters squared times speed in the nozzle. Okay, hopefully you can read that. So speed in the nozzle, so I'm going to take 5 10 to the negative 4, divide by pi, divide by 0.25 10 to the negative 2 squared. So, and again, 25.5 meters per second. So again, this makes sense because remember what we saw in the slide previously is that right when the area gets small, the speed has to get big. And in fact, that's exactly what we see in the example. So the nozzle has a smaller radius, so a smaller area. So the radius got smaller, and then the speed of the fluid got bigger.